Okay. Okay. Good morning. So today is our second session, and today we're going to discuss about polynomial regression, the first topic of the machine learning artificial intelligence algorithm that we will be discussing in this class. So let me share my screen. Okay. So here you go. So today it's about lecture number 2, polynomial regression. So what is polynomial regression? Regression from the keyword is just an estimation of some functions. Okay, there are, maybe you can, or this me are already familiar with linear regression. That means you are going to estimate based on a line of a certain function. But in this case here, we take it as a polynomial. That means a polynomial is what? Is a function that is based on several terms. Okay, not just one line, not just a linear function, but the degree could be higher. Okay, so in this case here, for example, we have an example of a sinusoidal function where an input is 2 pi of x, 2 pi x sine, and then that is the function, and this is the function here, the sine function, and the input is x. So the output is sine of 2 pi x. So this is x, and this is the output. And now there are this is the entire function, and now there are some noise or target values that are associated with this function. So the points here are the data points. Okay, and we say that in this case it looks like the data points can be on the line, for example here, exactly on the line, and some points here there's some not exactly in the line, but then maybe some noise, and some points are not on the line. So in this case we are saying that these points here are your values or your data. Okay, and this function here is an estimation, is some estimation. We don't know if it's a good estimation, but some estimation of this data here. And in this case, the function is that gives an estimate of the data of those points is the sine function 2 pi of x. Okay, so in our case here, there is a target value, is not shown here. Okay, here, let me annotate. Okay, so there is, this is x and that's t. So there is an x and a t value. Okay, so based on the x, for example, x goes from, I think, 0, what are these? Let's just say it's 0.1, yeah? 0, let's just say it's 0.1 increment, and then 0.2, 0.3, like that. Okay, up to maybe there's 0.5 and up to 1. Okay, so that's the table of values. There are some values here in between. Some values here in between. Okay, and now based on this function of x, I mean based on the input x, you have some value of t, and in this case maybe t is this 1, yeah, 0 to 1, so maybe 0.3 t. Okay, and this one is 1, maybe 0.8. And then this one is 0.2, maybe 1. And this is 0, let's say 0.3 here. And this is 0.9, like that. Okay. And around 0.5, where's 0.5? Maybe this one. 1, 2, 3, 4, 5. Let's just say this is around 0.01, maybe. And around 1, this is around maybe 0.1. Okay? So I'm just writing out here to say that there are physical systems. Okay, I would like to say physical systems because it's more clear to us that are under observation. Okay, for example, that these physical systems gives us certain values, certain characteristics as we record their, record some parameter given time. Okay, so for a particular time, for a particular value, for a particular input value of x, there is x of 0, there is a corresponding value, a measured output. This is like a measured output. Okay, given a certain input. Okay, we say the input here is x, yeah? So this is a given input. You come out with a measured output. Okay, so now what we have now is that based on this input, we measure a data. And now there is the output that becomes our data. And given this information of data points, we are going now to estimate. Okay, now we need to have an estimated output. Okay. Yeah. Okay. So we have, maybe I should put, these are data points, and the other one is, this is the estimated output. Okay, there's the real output and the estimated output. Now, the estimated output will depend on what kind of function did we use to estimate it. So in this case, we use the sine function to estimate, we say, the characteristics of the data points. Okay, we say that, hey, most likely the sine function makes a good estimate of these data points. Okay, so how do we measure goodness, or how do we measure the most likely function that gives a good estimate of the data points? That's the question that we are trying to address here in terms of regression. Regression, we're trying to estimate some function that will give us somehow a good value that will give us, in the absence of data points, or by removing the data points, we will be able to give out a good estimate of what could be the answer. For example, in this case here, maybe we'll say that this is 0 and this is 0.1. So what about in between points? 0.05, for example. We don't have a data point. Okay, so but absence of data point, the function that we use to estimate will give us that point. Okay, and in the absence of other data points, maybe in other places here, we can, that are beyond our estimated value, the sine function continues, right? And so now we can have a good estimate of the values where they are not covered by the data point 0. Our model is only based on 0 and 1. So if we go beyond that, so -1, for example, and -2, because we have already we have an estimated function, then we can give out an answer. What could be the answer at 0? Maybe -0.2x. X is equal to -0.2. Okay, so with that, that is the essence of having an estimated function, because it will give us some estimated values for points that are beyond the data points. Okay, so anyway, it is just an overview. So what I want you to listen or to take note in this first slide is that there is an input. Okay, there is this input value. Okay, and there is this measured output. Okay, a measurable output. And these 2 points are giving us, and these 2 parameters are the data points. Okay, and now based on these data points, we are going to make an estimate. We're going to make an estimated output. And the function is of the estimated output is that it will now give us, if we are confident that our estimated function is a good approximation of the data points, now we can give an estimate of data points that are beyond, that are outside that was given from the data. Okay, this point is not there in the data, this point is not present, and that point is not present, and also these points. Okay, so now the function estimation that we use will give us the value of what can probably by the data point at these points that are beyond those that we measure. Okay, that's the essence of having linear regression. Okay, let's go to the next slide. Okay, so the next slides will just give an emphasis of what I just said just now. Okay, so we have n number of observations, x. So our input data is this x, and then now let's just write it down so that when you write it, it will be more emphasized. So these are your inputs. Okay, is that you sending a message? Is there somebody wanting to something? Okay, those are your inputs, and these are, okay, these are your inputs. And your T, sometimes they call it a target value or the measured output. That's why they call it T, because that's a target value, or is the real value, or the measured. There's a reason for it to be called a target value. I will discuss with you later. Okay, now the goal is to exploit the training set to predict the value of T for some new value of X. Okay, so that's what I mentioned already. So there is to predict. So we have the keyword here to predict the value of T, because it is the T value that we wanted to know. Okay, for some new value of X. Why is it called new value of X? Because some points, some values of the input X that were not there in the data. So we were saying a training set. Okay. What is the training set? Training, meaning we use it to build our model. Okay. So let's make this keywords training. Okay. Training set, okay, is used to build model. Okay. Maybe I should have like a drawing of really what is going on around here before I jump into the details. Okay, so we have, if I draw a block diagram, we have this one. First, you have your data. Okay, so from your data, we use to build the model. Okay, we train. Okay, that model is built by what we call training. How is this training done? We will show you later. But yes, we use the data to build the model, and to build the process of building the model is called training. Okay. Once you have that model, now you use that model to predict. Okay. What is normally predicted? We predict the output. Yeah. So there is that output that we predict. Okay. And so I want to use the linear regression here because it is a much simpler example on how these three stages are being done, from the gathering of the data into the building of the model, and then the predicting of what is the output of that model. Okay, so we say inherently it is a difficult problem, but most of us have already experienced in previous mathematical computational numerical methods in mathematics, where you also give estimates of some computations. Actually, I think you have experienced already polynomial regression at some point, or linear regression. Okay, we're just making it giving it a new flavor here and tweaking it in such a way that it will be placed into the family of numerical methods of machine learning algorithms that will give us estimates of certain solutions. Okay, so now what I want you to understand is that these three sets, these three methods. First is the data that we collect. Second, we use that data to build a model. And third is that we predict the values of the output based on the model. Okay, so let's clear out the one, and let's go to the next slide. Okay, now a simple approach is about curve fitting in order to solve for that function of linear regression. And we have done this, you have experienced this, I'm sure, in some of your classes. So let's just revisit it in order for us to give somehow a background of what we are doing in machine learning. So in this case here, there is a polynomial function, and we use the data to fit into the polynomial function, or we find a polynomial function that best fits the data. Okay, or what degree or what kind of polynomial should we be using. Okay, so this is an equation of a polynomial. So naming first, we have to be quite consistent. We name the inputs of the polynomial as x, which is normally is also the input of the data points. Okay, we have the same input x, but aside from the input x, we also need an input of w. Okay, the w are what we call weights, and these are the weights, or in some cases we call them coefficients. So in here, in machine learning, normally we use them weights. Okay. Okay. So you have the input value x, input parameter x, and the weights. There are now two inputs in your polynomial function. And your function, this function, y of x and w, and y is the output. So now this is your output. The output, the output is, y in this case is the function. Okay, the output of this function, y of that function, is your output. Okay, Okay, now there are two other things that we need to know. Okay, so normally every term in the polynomial, that's why it's called polynomial, because there are terms. Okay, there are norms, there are terms here that are being added. Okay, several terms being added in a polynomial function. Okay, so is a line is a equation of the line a polynomial function? Yes, it is. There are two terms there for a polynomial function of a line. So in this case here, what about the constant value? Well, strictly speaking, it is not, because it is only one polynomial function. I mean, well, for example, if y of x not w, is that a polynomial function where you only have w0? It's a constant value. Is that a polynomial function? Well, strictly speaking, it is not, because it is just a constant. There's only one term. Okay, but we can also say that yes, it is a polynomial function where you have w1 0 in it, w2 with another function of 0 in it, w3. Those are all the terms that are all zero. Okay, anyway, so in our case here, let's assume everything is a polynomial function. We are dealing with all polynomial functions in several, because that is what we are most interested in. And the w itself, example for this constant, we can still consider it a polynomial. Okay, so it is a constant value, and then that has a characteristics of a polynomial function. Okay, anyway, so now here we have w. There are we have to look at the terms, the coefficients or the weights, this part, as well as the degree or the exponent of each of the terms, of the input terms. Okay, so this is the first term. You have the first component, I mean the first weight, w0, and your x is to the power of 0. Okay, any number to the power of 0, this value is just equal to
1.
Yes, that's 1 all the time. But anyway, we write it like this because we want it to be uniform. Okay, so that it's easy to do mathematically. Okay, now, I mean, in terms of symbols, we can write them in this symbol like form like that. Okay, now the next one is x to the 1. Okay, this is x and x squared and so on. Okay, so the m is the degree of the polynomial. We call it the degree of the polynomial, or the highest exponent. The degree of the polynomial. Okay, so we can see that the degree of the polynomial, the number of the degree, is also equivalent to the index, is equal to the index of your coefficient. Okay, so now that's why we can write it in a more compact form of a summation of all the wj's multiplied by x to the j. Okay, where your wj is your weight and j goes from 0 to n. So the same way as we write this coefficient here, we can write it in a more compact form, in a summation form, in this form. Okay. Okay, that's our polynomial. Okay, remember our polynomial compared to our data only has one input x. Okay, our data has one input x and an output t. Okay, but your polynomial function, okay, maybe I should. Okay, that's your output from your data. Okay, but for your polynomial function, you have input x as well as your w. Okay, before you output your y of xw. Okay, so there you go. Okay, this is your estimated value. This is your measured value or target value. And then this is estimated value. Okay, to come out with your estimate, you need the x as well as you need the weights. Okay? Because to build your polynomial function, and then you have the output y of xw. Any questions so far? So now let's have a feel, or like let's be confident, or let's be familiar with our symbols that we are using. So in this case here, we say your x, yeah, is a scalar input, one value only. Okay, your x is a scalar value. Okay, one value per in the graph, one value per measurement. Okay, this is scalar, but your w is a vector. Okay, w is a vector here. W, normally a vector, there's like that when you write it by hand. So it's w like this, to say that it is bold, and then it is composed of all those here, w1 to wm, w1, w2, and so on up to wm. So now in this case here, your w is a vector. Okay, that means it's composed of several components, of several, it's like an array or a vector with several components equal to the number of the degree of the polynomial. Okay, in some cases we consider this w0. So in some cases they call w0 as equal to a bias. Okay, where your w here will be plus a bias. In some cases your w includes the w0. Okay, starts with w0, w1 up to wm. Okay, I'm just giving you a feel of the polynomial. Okay, we're not yet doing the computation. Okay, for a function of the line, how do we write it? Well, you know, if you have a line function, okay, y, we always say y is equal to mx plus b, mx plus b. Okay, so in this particular form, well, we can write the line using our polynomial function equation. Y is xw. It will be, your b is that. So your b of x to the power 0 plus m of x to the 1. There, that's your equation of the line, the first two terms. Okay, okay, I think we're okay with that one. So let's move on to the next slide. So now let's move on. We're already confident about what a polynomial is and what the data is, and now we use the polynomial to estimate the data. Okay, so let's look at this graphs here. So the question is, what will be the good estimate? What will be a good representation of the polynomial? Okay, what is that? What will be the good estimate of the polynomial? What is the degree, or what is the order of the degree of the polynomial? Is the highest order always good, or the lowest order always worse? Okay. Well, we don't know. Okay. Let's say, for example, in this case, we have like n data points equal to 10. So that's what we said before. We have from 0 to 1 and with the increment of 0.1. Okay. In the x, so there are 10 points. Okay. Or, yeah, maybe 11 points. I don't know. If we do that from 0 to 1, okay, increment of 0.1. Okay. 1, we have, is that correct? And then red lines, we have the red lines as the estimate of the estimates of our polynomial function. Okay, we say what will be the good estimate of the polynomial function. Okay, in this case here, we are saying that the polynomial function here, what polynomial function will be a good estimate of the data? We are saying that this sine function here is already the good estimate. Okay, but now we want to use a polynomial function that we know, that function that we have been using, the order where we are more familiar with. Okay, we don't want to use the sine function at this time. We want to use a y is equal to that one, xw. Okay, in terms of w0, x to the 0, plus w1, x to the 1, and so on. And so on. Okay. Plus x to the m. W m x to the m. We want to use that function, a polynomial function. We don't, because that's easier for us to handle. Although we know that the sine function will give a good estimate, but we don't want to use it. We want to use, because in this case, well, it is just good because the sine function is the one that is being used to generate the data with some noise. That's how these data points are being generated. Okay, so the sine function is a good estimate, but it is not a polynomial function. We want a general polynomial function. We want a polynomial function to estimate any data points. That's why we want to use that, so that for any data points given, then now all we need to do is to look for the values of w and decide what is the degree that best fits the data points. Okay, so now we are saying here, there are the red lines are the ones, the polynomials that we use to test. Okay, so the first one has the degree 0, second one has degree 1, third one is degree 3, and the other one is degree 9. So which one best fits or give a good estimate of the data points? Okay, so now let's investigate. So when your degree m is equal to 0, so this is just like that. The first point here, degree 0. So it's a constant. So whatever is your w, so in this case, your w, this is always equal to x to the 0 is 1. Yeah, we say it's 1 already. So now this is just a constant w0. So in this case, our w0 is non-zero, so probably this is around 0.2. Let's just say this is around 0.2. Okay, so that's why your output is always 0.2, no matter what the value of x is. It's not anymore dependent of x because there's no x. Why? Xw input is always equal to 0.2. There's no x on it. No matter what x is, the value is 0.2. Going up, going down here, going down everywhere. Okay, it's 0.2. No matter what your x is. Okay, that is just a horizontal line. You understand? Okay, that's our first estimate. Do you don't understand? Okay, Mr. Howning, what is your question? Tell me before I move on.
I don't know, why is it 0.2 again?
I'm just saying that is I'm just estimating that is 0.2 because here in this graph, let me undo. Here, you see this one? 0 and 1. Okay, I'm just estimating that this is around 0.2. Okay, and to have this graph of 0.2 and m is equal to 0, okay, this is from the polynomial equation here. So we have this polynomial equation where your degree m is equal to 0. Because m is equal to 0, that means all of these are non-existent. Okay, we have m is equal to 0, we only use the first term, right? Is this understood? Yeah, we only use the first term. And because we use the first term, so you have y of x of w. Okay, when we write w, I should remind me, I should use w as a vector. Okay, equal to w0. Okay, because the other term is a 1. So now, what is that w0? Well, this is a general equation for a polynomial function with just one term. Okay, but in this case, there's a graph is already given. I'm just estimating that that is around 0.2. That's all. So if that is the case, then your line of 0.2 goes everywhere. It's always 0.2 no matter what the value of x is. Is that understood? Okay, any other question? Willard, you wanted to drop this course, right? This is your punishment for attempting to drop the course. Jason? Huh? No, we cannot hear you. Yeah, Jason, your microphone is off.
It wasn't that I wanted to drop it. We had just heard that maybe somehow it's not offered. So, and then we later heard that no, it's a very good course for a mechatronics student. So I added it again.
But we met already. We met the first time, and you're scared because you don't want to answer my question for attendance. I saw you, and then you dropped. I said, "Ah, Jason dropped." It's fine. Come on.
No, I dropped it like maybe 3 weeks ago.
Okay. It's okay. I don't take it personally. Come on. Even if you're
and then I added it three weeks ago again. I think I added it maybe 3 hours after I dropped.
Okay, come on, answer.
What was the question again?
I even forgot the question.
Yes.
So, do you agree that in this case, this is the line that goes no matter what your value of x, it will always be a horizontal line of 0.2.
Yes, I do agree.
Okay. So now,
yes,
you have a question?
No, I don't have.
Okay. Now let's go to the next line. Okay, let's delete that line. Okay, we remain with that one. Now we make our degree equal to 1. So now what is this now? What is this equation? With the degree is equal to 1, that means you're taking the second term. Okay, you take these terms here. Okay, I should make it another equation. This term. You agree? Degree m is equal to 1. There. we're taking m is equal to, in this case, we're taking m is equal to 1. So when m is equal to 1, then you take, because m is, it goes from something, yeah, this polynomial function, if you can see this equation here, m starts from 0 to some value m, okay? I mean, j starts from 0 to some value m. Okay, now, so in this case, m is the highest order, okay? The highest order is 1, so it always starts from 0. In this case, the highest order is m starting from 0, so there's only one term. So the highest is 1, and so starting from 0, so there are 2 terms, okay? So now you have this. So our equation in that case, when m is equal to 1, will be y of x input and w input, that's a vector, is equal to w0 x to the 0 plus w1 x to the 1. Tell me when it's already 12 o'clock, okay? So that we can have a break. Okay? So now we have 2 terms now. Previously, we only have 1 term, this term. Now we are now considering 2 terms. So what is these 2 terms again? What is this equation? It is a line. Okay? Well, sir, this one is also a line. That equation is also a line. This is also a line. Yes? What's the difference with that line and this line?
I think the difference is the gradient.
Yes.
The first one is a gradient of 0, and the other one is a gradient greater than 0.
Okay. Gradient can be anything. Can be greater than 0 or less than 0. Okay. It could have a negative gradient or a positive gradient. Okay. So now, okay, we know that this line can go like this. Yeah. Okay. Maybe this can have several lines. Yeah. Can go like this. Can also be like that. Yeah. Can also be here, right? Can be anywhere, yeah, as long as it's a straight line on the plane. So what about this one? What are the variations of this line? What are the variations of this line? The only thing that will vary is the value of 0.2, W0, right? If W0, depending on the value of W0, what will be the what will that line look like? Well, it could be somewhere here, up, depending if W0 is bigger. If W0 is bigger, so it's a horizontal line here. If it's negative, it will be down here. Okay, those are the variations of that line. Okay, there you go. Okay.
Yes.
Okay, understood. So, for example, we go back to this if only. Okay, let's. Now that we have compared the horizontal line against a general equation of a line, so let's go back to the first one. So if you're only given this line, this horizontal line only, where m is equal to 0, which one could be the best estimate of this function, do you think? I mean, which horizontal line is the best estimate? That's the question. Could it be this? Could it be this? Could it be this? Like that. Okay? So what I'm trying to show you is that even at this simplest, model of your polynomial function, you still have choices. Okay? You still have a choices.
Yes.
Many choices on which line, which horizontal line is the best estimate. There's nothing like I only have one choice, yeah? Just like in life, I have no choice. I took that, you know. No, there's always, in all situations, there's always several choices. Okay. You will say that you only have one choice because you chose that one. Okay. Anyway, so what could be the best estimate in this case? Well, because these points are generated from sinusoidal path, and the sinusoid is symmetric with respect to 0, depending, in this case, they don't have an offset. So now, maybe the best estimate is the horizontal line around 0 that passes through the 0 line. Maybe, you know. But how do we check it, if it is a good estimate or not? Well, later we're going to show how we check it, which estimate is the best estimate. Okay, but for now, let's keep in mind that you have choices, always have choices, even at this flat line, generating flat lines. We don't know which flat line or horizontal line is the best estimate. Now, so that means that in the line, now you see, when you increase your order of m is equal to 1, you have now many choices, including the horizontal line. Is that included? Of course, the horizontal lines are included. Those are lines. Those are still straight line. Now, in this case, with your gradient or your slope of the line to be equal to 0. Okay, that's still included. Those are among your choices, plus the other lines that have now the ability to turn around. Okay, turning around all these times, and offsetting also here. Turn and offset at the same time. There, you understand? You also have here like that. Yeah.
Yes.
Ability to turn and to offset. Okay, those are, and all of those lines, which is the best estimate of those data points that you have. Okay, so that is the case of n is equal to 1. M is equal to 1. Now, what is the case when you have m is equal to 2? Or in this case, m is equal to 3. Okay. So here, what is m is equal to 3? What is that function? What is that function? How you call it? When m is equal to 1, what is that function called?
It's a linear function.
Linear equation.
When m is equal to 2,
It's a quadratic function.
Quadratic.
yes. When m is equal to 3,
Polynomial.
It's a polynomial.
no. I mean, it's a polynomial. There's a more specific answer. M is equal to 3 is what? It's a cubic function. Cubic.
Oh, yes, cubic function.
Yes, very good. So a cubic function, the
Yeah,
characteristic
it's a
of a
cubic
cubic function is that there is this turn, you know, there's this change in the turning. Okay, remember in the quadratic function is always like that. Yeah, there's only one turn. It's either turn upwards, turn downwards, or turn somewhere. There's only one turn. But in the cubic function, you make one turn and then you turn again. Okay, it's like you have another degree of freedom of turning. Okay, so a degree, the more degree you have, the more degrees of freedom that your function can move. Okay, so now you have this ability to turn. So it goes up and then it turns and goes down and turns again. Okay, so in this case, it looks like it follows the data points, right? But then again, you have many choices of that turn. Okay, so what are those choices? Well, we know already. So this could be one choice like that. It could go down like this. Or it could be another choice like that. Or it's like an S choice like that. Or somehow another choice here. It goes like this. like that, yeah, or another function inverted the other way. Could go down first before it goes up. That's also a choice, okay, although not the best choice, but still, you know, if there are no other choices, maybe the worst choice is the best choice. Okay, anyway, so you can see all these other possible lines, all other possible cubic functions that could be a good estimate of this, of the data points. Okay, so how do we change all these? How do we make all these different kinds of cubic functions, or different kinds of lines, or different kinds of flat line, horizontal lines? How do we make them behave like that? How to make them behave differently? Well, the behavior or the graph of those functions change depending on the coefficients. Do you understand, Chepo? You have questions, Chepo? I see your
No, so there's no questions. Sorry.
yeah, you can ask any question. Okay, you can make me stop if you have questions. So we have to go back to the coefficients. So these coefficients, the x, well, the x change, yeah, but then those are just input values here. Okay, but the w's will give characteristics of the function, will give a certain characteristic of the function depending on what is your value, the value of the w's of your weights. It will make into a different function, okay, a different line or a different graph. For example, if you're in this case w0, change in w0 for the first case of m is equal to 0, we'll have a different line. This line, although horizontal line, that line, and that line, okay, depending on what your value of w0 is. So the same thing in the line. So depending on the value of that, in this case, when m is equal to 1, depending on the value of your w0 and w1, your line will change, okay? So if you play around with these weights, these values, your lines will change. We'll give it a different line. We'll give it another line, okay? So the same thing as here in your cubic function, depending on your w0, w1 up to w2, so w2 x squared plus w3 x cubed. Now, how many w's you will be playing with? w0, there are 4 w's that you will be playing with. You're playing with 4 parameters in order to give you some cubic function that will give you the best estimate of this. Okay, depending on what is the value of w, it will be the graph of your cubic function. Okay, let's stop first from here. We will continue after 10 minutes. Okay. Okay, keep your, take some water.
Yes, sir.
Also take some water.
Say,
Yes, questions?
We wanted to know if we can move the class to 8 o'clock.
8 o'clock on Friday.
Yes, sir.
Is
I have
everyone
a class
agreeable?
then.
I don't have a problem. Is everyone
Yes, sir.
agreeable?
No, sir.
No, I have a class with another module.
Yeah. We can
Agar salir discuss kami malo wal didime lesa bu.
Naigawan nagutan ka kanyalon.
English is our official language. Come on, let me know what you're talking about. What is it? Okay, let me stop the recording first because